So the topic for 2.3a is the word continuous. And I'm going to start out with an informal definition, but I want to emphasize that this is not the definition that you use to answer questions. This is just kind of, well, it's informal. So anyway, a graph or a function is continuous if you can draw the graph without picking up your pencil. A graph or a function is continuous if you can draw the graph without picking up your pencil. So if you think back to the graph of sine of x, that's a wave like this. That's continuous because you could draw the whole thing without picking up your pencil. Okay, but again, this is not, if there's questions on tests or homework or anything that say, is the function continuous? You can't say, it is because I didn't have to pick up my pencil to draw it. So the definition I'm about to give you, the formal definition, is the one that you need to work with more. Okay, so this is the formal definition of continuous. A function f of x is continuous at x equals a function f of x is continuous at x equals a when the limit as x approaches a of f of x, so you can see why this is a calculus definition because it's got a limit in it, is equal to f of a. The function f of x is continuous at a when the limit equals the function value. Okay, so to get at that, we're going to look at some questions. So I'm going to draw a graph here. The graph is going to have an open circle at 5, 2. And then it's just a straight line going down this way. Then it's going to have a filled in circle at 5, 4. And it's a straight line going that way as well. Okay, so first of all, informally, why is this graph or this function not continuous? Yeah, because you got to pick your pencil up, right? So I had to draw this piece of it, and then I had to pick my green marker up to go up here to draw that other piece of it. So it's clearly not continuous. Okay, but we need to think about why it's not continuous from this perspective. Okay, so where does the problem occur? At what x value does the problem occur? Right, exactly. It happens here right here. So where we suspect that it's not continuous is at x equals 5. So we're going to calculate the limit towards 5, and then we're also going to calculate f of 5. All right, so we're going to calculate the limit towards 5. And we're also going to calculate f of 5. And we are suspecting that these are going to be different answers, because we think it's not continuous at 5, right? And according to the definition, if it was continuous at 5, these would be the same. So if they're continuous, the limit is the same as the function value. So we're going to investigate, and we're thinking that this is going to be different than that, because otherwise it would be continuous. Okay, this is easier to calculate, so let's start with that. F of 5 means give me the y value at 5. So that just means go over 5, and then I can tell that the dot's up there at 4. So f of 5 is 4. On the other hand, let's calculate the limit towards 5. So we need to pick some numbers that are close to 5. So 4.9 spits out this value here, right? Which is maybe 1.9. That's not, finding that y value is not an exact science. I'm just going over 4.9 and I'm saying, okay, well that's not quite up 2. Because the open circle's at 2, right? So it's just a little bit below 2, that dot. Okay, and then 4.99 is not quite 2, but closer to 2, so 1.99. So that tells us that the limit from the left side is 2. And then 5.1 is up here at about 4.2 maybe. And then 5.01 is up here at maybe 4.1. Again, these y values are not exact, I'm just approximating. But what are those getting close to? 4. Okay, so the limit from the left side is 2, and the limit from the right side is 4, so that means the overall limit doesn't exist, right? So this limit does not exist. And then does not exist equal 4? No, it doesn't. So that's officially why it's not continuous at 5, because the limit has a different answer than the function value. Okay, so since the limit, as x goes to 5, of f of x doesn't equal f of 5, now we know that it's not continuous at 5. Since the limit, as x goes to 5, doesn't equal f of 5, that tells us that f is not continuous at 5. And we could tell by looking at the graph that it wasn't continuous, because informally that's where we pick up our pencil. But the official way to say it is since the limit doesn't equal the function value, that's why it's not continuous. Okay, this type of a discontinuity is called a jump discontinuity. The reason it's called a jump is because you have to jump up here to draw the rest of the graph. So this is called a jump discontinuity. So it's not continuous, so it's called discontinuous, or a discontinuity. And this is a special type of discontinuity called a jump discontinuity. All right. How about this graph here? So there's going to be a vertical asymptote in this graph. And it's going to look like this on either side of the vertical asymptote. The vertical asymptote's at 3. And then there's a dot at the point 3, 1. So this always bothers people because they've been told that you're not allowed to touch an asymptote. It's not completely true. Like I said yesterday, you're learning more of the truth now that you're in calculus. So I'm allowed to put a dot there at 3, 1. It's part of the function. And then there's a couple of pieces over here. Okay, so looking at this graph, where does it look like it's not continuous? At x equals 3, right? So you have to draw this piece, and then you have to come here and here to draw that dot, and then you have to draw this piece. So at 3, there's a problem. So we suspect that it's not continuous at 3. So what should we calculate to confirm or deny whether it's continuous at 3? F of 3, first of all, right? Okay, good. So in order to investigate continuity at 3, we want to calculate f of 3. What else do we want to calculate? Probably a limit, right? Because we're in calculus class, so we're going to calculate the limit as x goes to 3. And we are suspecting that these are going to come out to different answers, right? Because we think, based on the graph, that it's not continuous at 3. And if these come out the same, that means it is continuous. So we're hoping, we're thinking they're going to come out different. Okay, so I put a dot here at 3, 1, right? So f of 3 is 1. Some of you are doubting whether I'm allowed to do that or not. I understand. I'm allowed to. Okay, so f of 3 is 1. Okay, now what is this limit? What's going on with this as it comes from the right? It's going to infinity, right? And on the other side, it's going to positive infinity. Okay, so this limit is infinity. Does infinity equal 1? Definitely not, right? So that means these are not equal. So since they're not equal, that confirms that it's not continuous at x equals 3. Okay, so what's going on here is there's a vertical asymptote because the graph is going to infinity. So this type of discontinuity is called an infinite discontinuity. And basically an infinite discontinuity happens when the limit is infinity or negative infinity. So if there's a vertical asymptote, that's going to cause an infinite discontinuity. And I commented in one class, I'm not sure I did yesterday, your calculator sometimes connects these, right? Because it doesn't understand discontinuity. And so it just draws a bunch of dots and connects them. Because it can't conceive that there'd be a hole there. But we're more sophisticated than that, and we know that there's actually a space there and it goes up to infinity. So we know not to connect them. I don't know if you've ever been to Mexico, but if you go, don't drink the water. Because if you do, you may get an infinite discontinuity. Because it causes problems. Sorry, I'm telling a really bad joke. A really gross joke, right? Because if you're having bathroom problems, it's called incontinence, right? So it really doesn't fit, but anyway. So don't go to Mexico and drink the water because you'll get an infinite discontinuity. There'll be a calculus problem. Even in Mexico, you can't avoid them anywhere. So I think that was my first really bad joke of the year. There will be more. Don't you worry. I know that after that, you're really hoping that I'll tell a lot like that because they're so hilarious. Don't worry. There's plenty where that came from. And I tell the same ones every year. So Zach's hearing them all for the second time, which he is very, very glad about, because they were so good the first time. Yes, just for the jokes. Yes, yes, yes. Okay, let's see. What else we got? So we had an infinite discontinuity and a jump discontinuity. And there's a third type of discontinuity called a removable discontinuity. Okay, so a removable discontinuity happens when the limit as x approaches a of f of x is a number. So that didn't happen here, right? Here the limit didn't exist. So it couldn't be a removable discontinuity. And also here, the limit was infinity. So it couldn't be a removable discontinuity. So a removable discontinuity happens when the limit is a number, but also f of a is not that number. It's a different number. Okay, so that didn't happen over there. Those were a different type, but this is the third type of discontinuity called a removable discontinuity. So let me show you an example of that. So this would be example 3. And our function is going to be f of x equals x squared minus x minus 6 all over x plus 2. And the question is f continuous? And then if it's not, classify the type of discontinuity. So is f continuous? If it happens to not be continuous, classify the type of discontinuity. And then if the discontinuity is removable, extend the definition of f to make it continuous, to make a new function that is continuous. So sorry, long directions here. If f is f continuous, so we got to answer that question like we have been. Classify the type of discontinuity if it's not. So that'll be either jump, infinite, or removable. Those are our 3 types of discontinuities. And then if the discontinuity happens to be removable, extend the definition of f to make a new function that is continuous. Okay, so I'll show you how to do that if it happens. Okay, so looking at this function, where do you think there might be a problem? Yes, Zach. -2. Why is he suspicious of -2? Yes, Michael. Because it makes the denominator 0, right? And dividing by 0 is often a problem. Okay, so we suspect that maybe at -2 there might be a problem. So these were easier to tell where there might be a problem because we actually had the graph, right? so we could see where the jump was, or we could see where you had to pick up your pencil. So when you just have a function, it's a little bit more complicated. But dividing by 0 is generally a problem. So we suspect maybe it's not continuous at -2. All right, so we need to calculate the limit as x goes to -2. And then we also need to calculate f of -2. And if it's continuous, what will happen? They'll be equal. Good. And if it's not continuous, then there'll be different answers. Okay, so let's start out with the limit, because that's the harder one. So limit as x goes to -2 of x squared minus x minus 6 all over x plus 2. We're trying to calculate the limit towards -2 of our f of x. Okay, so we got our list of ways to calculate limits. We like to avoid tables if we can, because those are a little unsophisticated. They're fine to use, but we'd like to try other methods if we can, especially if we don't have a calculator. We can't use a table method. So then there's limit laws, right? So we could do the limit of the top and the limit of the bottom separately. What happens if you do the limit of the bottom? Comes out to 0, right? The limit would be in front of this x and in front of that 2. The limit of that is -2. And the limit of that is 2, so the bottom would come out to 0. Is everybody okay with that? Not just, I'm not plugging in -2, right? I'm taking a limit, different thing. Okay, so anyway, limit laws don't work because the bottom comes out to 0. Okay, so what else, what other methods do we have? Yeah. There's factoring, right? Good. That looks promising on this one, right? Because sometimes we can factor that. There's clear double fractions, which doesn't happen on this one, right? Because there's only single fractions here. Nobody's married yet in this problem. Just single fractions. There's my second bad joke. Okay. So then there's rationalizing, right? But rationalizing usually comes up when there's square roots in the problem. So I don't think that's going to happen here. Let's see, sine of x over x, that limit as x goes to 0 is 1, but there's no signs in here. I'm just kind of reviewing all of our methods, right? Squeeze theorem or sandwich theorem, I'd rather not do that. I did that yesterday during class. It was a pain enough then. Okay, so anyway, Krista's exactly right. Factoring is the way to go on this one, because the top factors. Okay, so factors into x minus 3 and x plus 2. So that's good news, because then the x plus 2's cross out, right? And remember, we had a big philosophical discussion about whether you were always allowed to cross those out. The reason you're allowed to cross them out is because something divided by itself is 1. But it doesn't equal 1 when it's 0 divided by 0. But that's okay, because it's not 0, because x isn't -2. It's something close to -2. So we're definitely allowed to cross those out. Okay, then limit laws, limit of x and limit of -3. So moving the limit past the minus now. What is the limit of 3? Oops, I miscopied this, didn't I? Sorry about that. What's the limit of 3? 3, right? The table is -1.93, -1.993, and so these are getting close to 3. And then here the table is the y is always equal to the x. So -1.9, -1.9, -1.99, -1.99. So these are getting close to -2. So this answer to this limit is -5. So we calculated this limit without a table using the method of factoring. Okay, how about f of negative 2? What happens if I actually plug negative 2 into this function? I get undefined, right? Because I'm not allowed to divide by 0. So f of negative 2 doesn't exist, or it's undefined. So does this limit answer equal this function value? No, it doesn't, so that confirms that it's not continuous at negative 2. So we calculated the function value, we got undefined. We calculated the limit, we got negative 5. Those are not the same answer, so that's why we know that it's not continuous. Because the limit doesn't equal the function value. Okay, so that answers this first question. Is f continuous? It's not everywhere. It's continuous at most places, but it's not continuous at negative 2. So the answer is no. Okay, then it says classify the type of discontinuity. So there's 3 types. There's jump, infinite, and removable. A jump happens, an infinite happens when the limit is infinity. Is that happening here? No, the limit's negative 5. Okay, then a jump happens generally when the 2 limits from the different sides are different. So it's not that, because the limit is equal to negative 5 from both sides. Okay, so probably it's removable, which you probably already knew because I just introduced that. But let's digest this. So is the limit a number? Yes. And does f of a not equal that number? Yes, so that's why it's a removable discontinuity. Okay, so this is a removable discontinuity. I think I'm spelling removable right, but for some reason this morning it's looking weird to me. Removable, but I think that's right. So this is a removable discontinuity because the limit came out to a number, but f of a wasn't that number. Okay, so now we're to the last part, which says if the discontinuity is removable, which it is, extend the definition to make a new function that is continuous. Okay, so I've got to make a new function. I guess I'll call my new function g of x. And f of x is continuous at most places. So I'm going to keep this function for my new function most of the time. Okay, so my g of x is going to be a piecewise function. So it's going to have 2 different formulas. And I'm fine with this formula as long as x isn't negative 2. So I'm going to instruct the reader to use this function whenever x isn't negative 2. Because the function was just fine as long as we weren't at negative 2. It was continuous. Okay, but I need something to happen at negative 2, right? Because I can't plug negative 2 into this function. So I need to make a new function that is continuous. Okay, now what is the limit of this function at negative 2? We already calculated it, right? The limit of my new function towards negative 2 is negative 5. because I'm using the same formula for my new function. Okay, so what do I need g of -2 to equal? I need it to equal -5, right? Because I need my limit to equal my function value. So I need a formula here that spits out -5. Because then, if I calculate the limit of this, I'll get -5. And if I calculate the function, I'll get -5. So then I'll have a new function that's continuous. So I need to come up with a formula that spits out -5. Here I'm going to come up with a really complicated formula that spits out -5. There it is. Just tell the person that at -2 it's supposed to equal -5. Now if you don't like that, you could put x plus 2 minus, let's see, -2 plus 2 is 0, -5. X plus 2 minus 5 if you want, right? Or you could put x minus 3. Whatever formula you want here that spits out -5 would be just fine. Okay, so now I have a new function called g of x, where if I calculate the limit at -2, it comes out to -5. And if I calculate g of -2, it also comes out to -5. So this is a continuous function. So I extended the definition, meaning I added a little bit of piece. I made the function a little bit longer and made a new function that was continuous. Is everybody okay? That's why it's called a removable discontinuity, because pretty easily I can get rid of it and make it continuous. If I just do one more point than that function, then I've got a continuous function. Okay, it's early in the morning, so you might have missed some of that. So ask a question now if you need. Remember, I'm impressed when you say that there's things you don't know, because I'm sure there's somebody else in the room that feels the same as you. Nobody has any questions. Okay, I think I said everything I need to say, but I got to come over here and check my notes. Yeah, I think we're good, so that's it for today.